In this paper, we propose a method for constructing families of models with equal numbers of parameters but varying depths. Our primary algorithm involves adjusting the depth of the models while maintaining a consistent attention mechanism across all models. This approach allows us to explore the impact of depth on model performance and generalization in a controlled manner. We also derive hyperparameter relations to calculate the necessary adjustments in the feed-forward dimension when adding or removing layers. By using initial values from existing size classes of models, we can determine how much the size of the feed-forward dimension must change based on the number of layers. This ensures that the models in each size class have equal numbers of parameters. Our findings indicate that increasing model depth results in a significant improvement in perplexity, especially at the shallow end of the spectrum. Deeper models generally outperform shallower ones, with the perplexity of a single-layer model being nearly twice that of the optimal model in the class. However, the performance boost from adding layers diminishes rapidly as models become deeper. We also observe that deeper models tend to generalize better than shallower models on compositional generalization tasks. The benefit of depth is more variable across different tasks, with some tasks showing threshold depths after which generalization accuracy remains relatively constant. The impact of depth on compositional generalization is more pronounced for lexical generalization tasks compared to structural generalization tasks. In terms of performance on structural tasks, deeper models do not significantly improve the model's ability to learn the correct inductive bias. The benefit of depth is largely limited to easier lexical generalization tasks, while structural generalization tasks show less improvement with increasing depth. Larger models are more robust to changes in the feed-forward ratio, allowing them to become wider in proportion to their model dimension without incurring large penalties in perplexity. Conversely, smaller models are more sensitive to the particular value of the feed-forward ratio, and the standard ratio may not be optimal for them. Our approach primarily focuses on models that are shallower and wider than standard convention. The disparities between the shallowest models in our approach and conventional models grow as the size class gets bigger. Our approach allows for exploring the impact of depth while controlling for total parameter count. We also correct for potential confounds such as lower pre-training losses and better in distribution performance of deeper models. Even after adjusting for these confounds, deeper models still generalize better than shallower models, indicating that depth directly improves generalization. We acknowledge limitations such as the lack of multiple runs for each condition and the potential confounding effects of the pre-training corpus. We suggest future research directions, including exploring in-context learning, controlling for the distribution of pre-training data, and investigating the impact of including source code in the pre-training corpus.